Hello, everybody. Will be a discussion of canonical quantization in quantum field theory. It will be followed by a discussion about cross-section, scattering, and Feynman rules and Feynman diagram in the following weeks. Okay, so today we'll concentrate on the starting point of quantum field theory. I usually say it is the essence of particle physics. The key idea is that particles are not like balls, as we expect in Newtonian mechanics, but they are essentially fields. The reason, of course, is special relativity. We have a relativity invariance, so therefore the picture of balls with specific position does not apply here. Therefore, to accommodate relativistic invariance, the physical system must be expanded just like fields. But well, not quite, because they are not, particles are not classical fields. They are quantum fields. And the key point I want to make today is that quantum fields turn out to be quite like balls. Okay, that's an interesting statement, and we will see very soon. Okay, so now this is a table I got from Professor Coleman's quantum field theory course, which show the relation between the various theory. Here is quantum field theory, and I will show you today that it is very easily derivable from classical field theory. I assume that you are familiar with classical field theory already. For example, the Klein-Gordon equation and its Lagrangian and Hamiltonian form. And so therefore, we would like to model the transition from classical field theory to quantum field theory by the procedure, the transition between classical particle mechanics and quantum particle mechanics. By classical particle mechanics, I mean things like Newtonian mechanics, and by quantum particle mechanics, I'm referring to the Schrödinger equation like quantum system, which is non-relativistic. This procedure from classical particle mechanics to quantum system, we usually call it canonical quantization. So we would like to model the transition from here to here. Oh, sorry. We would like to model the transition from here to here by the transition from here to here. That's the key idea. Okay. So let me first introduce the transition between classical particle mechanics and quantum particle mechanics. Actually, the procedure is very, very simple. We call it canonical quantization. First, you upgrade all the observables to operators. Okay, and usually we put a head. For example, in particle mechanics system, we usually have a coordinates, and then we have a conjugate momentum. And then in classical particle physics, all these observables, because they are observable, therefore they are numbers. However, we learn in quantum mechanics that in quantum mechanics in the microscopic world, they could not be just numbers. They need to be upgraded into operators. And if they are operators, they do not commute as we wish for the numbers. Therefore, we usually impose a commutation relation between position and the momentum, just like this. That is, the commutation between coordinates and coordinates is equal to 0. And the commutation relation between momentum and momentum will vanish as well. However, the commutation relation between Q and P, position and momentum, is not equal to 0. It is equal to I. Okay. This is called a canonical commutation relation. Canonical commutation relation. And this procedure, by imposing this, And we can, by imposing these commutation relation, we can transition from the classical particle mechanics to quantum particle mechanics. Let me interrupt for a moment to check if I have the recording procedure right. Just give me 1 second. Yeah, it's perfect. So let me continue our discussion. And from this canonical commutation relation, almost everything in quantum particle physics could be derived. So therefore, that's why the canonical quantization is very, very important. Let me illustrate the importance of this computation relation by discussing quantum simple harmonic motion. Sometimes I call it quantum spring. Okay, quantum spring. But this is the simple harmonic motion is one of the most important system in physics world. And by quantizing it, actually you will find very surprising result in the end. Okay, so let me start with the classical simple harmonic motion. In classical simple harmonic motion, we can write the Lagrangian in terms of T minus V, the kinetic energy minus the potential energy. Okay, for simple harmonic motion, the potential energy is just 1/2 kx squared. And I can rewrite this relation by introducing a new coordinates so that it looks simpler. Q is defined as this, a constant vector times x, and therefore then the second term could be written as 1/2 omega q squared, and the first term could be written as 1/2 q dot squared over omega. These are just arithmetics. Therefore, you can try to derive all the details at home with the transparency I gave you. Okay, so I would not go into detail about all this mathematical derivation. Sorry about that, but because I don't have a blackboard to write, therefore, and all the mathematics are pretty simple. I want to concentrate on physics during our lecture. Okay, so then with this Lagrangian, we can continue to, we usually, the conventional procedure is to derive the Hamiltonian from this Lagrangian. To derive the Hamiltonian, you need to first derive the momentum that we call it conjugate momentum. And in this case, the conjugate momentum is equal to q dot omega. So that means this P is almost like the conjugate momentum is almost like the momentum we expected from Newtonian physics. And then H could be defined as q dot P minus L. And therefore, with some mathematical manipulation, you can derive that the Hamiltonian H is equal to 1/2 omega P squared plus Q squared minus 1. Okay, so that's the classical mechanics. And with this classical mechanics, you can continue to derive how the Q will evolve in time. That is, we can derive the equation of motion, but that's too simple. We will not repeat here. So now we will proceed into the quantum world. I now quantize this simple harmonic motion. And the condition, the procedure is just as I have outlined here. You upgrade everything into operators and then impose the canonical commutation relation. Okay, it's this simple. So here the commutation, these P and Q now are upgraded into operator. Usually we give it a head. However, I don't know why I didn't write a head in my transparency, so bear with me. So from this point on, they are operators. And then I impose the quantization condition, which is a commutation relation between P and Q. Because now we have only one P and one Q, so the relation is simple. It's just P and Q. The commutator between P and Q is equal to minus I. Here I define H equal to 1 so that the notation will be simpler. Now, to proceed further, I introduce a set of linear combination of Q and P. we call it A and its complex conjugate, A dagger. So A is defined as Q plus IP over square root 2. A dagger is defined as Q minus IP square root of 2. And the quantization condition between P and Q will directly give you the commutation relation between A and A dagger. Actually, the relation, the logic order are two ways. That is, this relation, commutation relation, is equivalent to the commutation relation I gave you between A and A dagger here. That is, you can derive from here to here. You can also derive from A and A dagger commutation relation to the canonical quantization condition. Okay, but anyway, the result is that the commutation relation between A and A dagger is very, very simple. A and A dagger is just equal to 1. Usually, the commutator between two operators consists of operator. So if it becomes a number, then that's a big thing. Okay, so A and A dagger commutator, the commutator between A and A dagger equal to 1 is actually very significant. But the significance of, so please do the derivation yourself. And this procedure is actually standard material in almost all the quantum mechanics textbook. You can also consult them. You can very easily find the discussion of this procedure. But let's proceed further. And next step, we can go ahead. Now we have the commutation relation between A and A dagger, and I would like to write the Hamiltonian in terms of A and A dagger. Okay, but it's actually quite simple. That's why I make the choice of the relation between PQ and A dagger. So if you plug in these two relations into the definition of Hamiltonian, then you can easily derive H is actually equal to omega A dagger A. And with this relation, then you can go ahead to derive the commutation relation between H and A dagger. Here, I write down the very useful commutation relation formula about A, B, and C. It could be derived from A and the commutator of BC plus the commutator of AC times B. So you just plug in and you can easily derive. The commutator between H and A dagger is omega A dagger, while the commutator between H and A is equal to minus omega A. Well, it's pretty dry mathematics, but it's actually very a lot of fun to do the derivation yourself at home. Okay, so I urge you to do that. But here, I just want to emphasize the importance of these two relations in the following page. Okay, then the significance of these two commutation relations is that we can use A and A dagger. Let me give you the conclusion first. We can use the A dagger and A to raise the energy by 1 unit of omega and use the A to lower the energy by 1 unit of omega. So therefore, A dagger is called raising operator, while A the lowering operator. Not the cornerstone of the quantum spring or quantum simple harmonic motion, and will become the cornerstone of quantum field theory in just about 20 minutes. Okay, so let me do a little bit derivation as to why the statement I made here is correct. Now assume that we have a Hamiltonian eigenstate E with eigenvalue E. Then that means H acting on E is equal to the number E acting times the state E. Now I put a dagger acting on the eigenstate E as here. We form this state, quantum state. And then I check if it is the eigenstate of Hamiltonian. To do that, I just act H on A dagger E. And H acting on A dagger E, I can push this A dagger past H so that this H will act on E directly. See, because E is the eigenstate of H. However, there is an A dagger in between so that H cannot act on E to give you just a number. Therefore, I pass this A dagger through to give you A dagger H E. However, passing through two operator, that you need to compensate the difference with the commutator. That's the definition of this thing. Okay. However, H A dagger, we know the number. We know what the result of the commutator. We know the commutator, right? Because it's right on the top of our page. Okay. So H A dagger is nothing but A dagger itself multiplied by omega. Okay. So therefore, this commutator acting on E is actually A dagger acting on E. That's the state, quantum state we are talking about here. Okay, and the first term, H acting on E, directly give you a number because E, state E, is an eigenstate of the Hamiltonian. Therefore, we got a number E. Number E could be switched to the front, and then we got, again, A dagger acting on E, the same as the second term. Okay, therefore, put the two results together, it is equal to E plus omega. Remember, in this expression in parentheses is a number. Okay, is a number. And then this number times A dagger E. So put the equation together, H acting on this state is equal to E plus omega acting on this state. Therefore, this A dagger E is an eigenstate of H with eigenvalue E plus omega. Remember, E is the eigenstate with an eigenvalue E, so A dagger raises the eigenvalue by A omega. That's the result I have been advertising. Okay, so the operator A dagger can be used to raise the energy by 1 unit omega. Proven. Okay. The second part, the A could be used to lower the energy by 1 unit. You can do it yourself. The result is here, and it could be derived through very similar derivation as this expression. Okay, so I hope after this derivation you are convinced that, again, A dagger is the raising operator and A the lowering operator. Here I have a cartoon here depicting the various energy states, and with A dagger you raise the energy by 1 unit of omega, and then with A you lower the energy by 1 unit of omega. Okay, so that's a very significant result. It shows you that the energy spectrum or energy eigenstate of Hamiltonian are step-like, or in jargon, quantized. Okay, so that's the very neat, very neat derivation of the original energy quantization condition derived by Planck in 1900. Remember, the first gun in the quantum mechanics revolution is that Planck showed that for simple harmonic motion in the quantum state, in the quantum simple harmonic motion, the energy is quantized just like this. Okay, but he used a very complicated way to show to arrive at that result by going through the black body radiation, etc. But here, from the canonical quantization condition, we can derive. Remember, we haven't gone into detail about how to describe the simple harmonic motion. We didn't write down the Schrodinger equation. We didn't use the wave mechanics. We only use the state, the Hamiltonian, and the quantization condition. Okay, so that's the very neat and very significant way to show you that the quantum simple, the key result of a quantum simple harmonic motion. Okay, so it also illustrates that the wave picture is not necessary for quantum mechanics. Here, I didn't use any wave picture, right? So this quantum simple harmonic motion doesn't need to be the wave of an electron or anything else. Okay, so the only thing we need is the quantization condition. Okay, the quantization condition Q and P commutator equal to IH bar. So that's the significance of this condition. Okay, I hope you grasp the significance here. Okay, so anyway, now with this result ready, everything else will follow from here. So first, I would say that we can lower the energy by applying A repeatedly, but it must be stopped somewhere because you cannot the energy must be lower bound. Okay, so you cannot keep going. Okay, therefore there must be a state which when you use A acting on it to lower its energy, you will give you 0. Okay, so this condition will give you a state. This state we'll call it the vacuum, or ground state. The reason is that if you calculate where is that? Oh, here. If you calculate the Hamiltonian of this state by you acting H on 0, then you got exactly 0. So that means this 0 state or ground state is actually an eigenstate of the Hamiltonian with eigenvalue 0. Okay. Okay, so that's good. So we got the ground state already, which is the state with the lowest energy, And then from this lowest energy state, we can raise the energy by applying A dagger. Remember, A dagger is the raising operator. Therefore, if you act A dagger once, you got a 1 state. You act in A dagger twice, you got a 2 state. 2 state means there are 2 quantum energy. Okay, you are 2 quantum energy. So we usually just we usually call this multiplicity of the number of acting A dagger as the number of particle. Okay. So therefore, the conclusion I write it in red here is very, very important. You can go ahead to check the detail and enjoy all the mathematics here. But the bottom line, the result conclusion is clear. Quantum simple harmonic motion does look like a particle system. It's a particle, okay, and with changeable number. Yeah, it's very, very good because in modern particle physics, one of the first results we notice is that the particle could be created and annihilated, in contrast to the classical idea of particles. In Newton's time, he also anticipated all the material are made of particles, fundamental particles. However, in Newton's mind, or in the minds of classical physicists, they usually perceive these particles as could not be eliminated. They will be there forever. They are eternal stuff. Okay, so there usually is an implicit assumption that the particle number could not be changed. And it is also true in Schrödinger equation. Remember, in Schrödinger equation, we also assume that the total number of probability is equal to 1. Therefore, this particle could not disappear, and that we could not create a particle in Schrödinger equation. However, we know right away in modern particle experiment, particle could be created and particle could be annihilated. That's why this quantum simple harmonic motion is the thing, is the system, is the paradigm we can use to describe the modern particle physics. Okay. Okay, so now we have finished. There are some detail you can check by your own about the normalization of this state, but we will skip this part, and then we want to go directly to quantum field theory. Okay, if you understand the past 30 minutes well, the quantum field theory is actually a piece of cake. Very, very simple, the essential of it. Okay. Let me check again if I'm really recording. Yeah, I think I'm recording so that the result will be preserved. Okay, let's continue with quantum field theory. To emphasize that the quantum field theory is very, very simple, so I will go very, very fast to get to the key result. Maybe I'll come back next time to give you some more detail, but let me do a little bit faster so that you will see that quantum field theory is actually very, very simple if you understand quantum simple harmonic motion well. Okay, so as you already know, the quantum field theory, the field is a function of space-time. So, for example, we'll concentrate on Klein-Gordon equation, Klein-Gordon field, phi. Okay, so it is a function of x mu, the space and time 4 vector. So the first step is again to quantize the field. The first step is to promote the observable. Here is the field. So promote the field phi into an operator. For example, you can give it a hat, so phi becomes an operator. Just like the particle physics, you promote an x or q into q hat. Then, after that, you give the canonical quantization, the canonical quantization condition. And here it's simple because remember that in this case, the x space coordinates x vector are actually indices. Remember, the picture of the field is that you divide the space into small cube. And every cube, there is a field on it. Therefore, it's almost like a multi-dimensional particle system. That is, every field, each field at a specific point is actually a dynamic system, which could be a particle, for example. Okay, so the x is actually corresponding to I, the indices. Therefore, if for classical particle system, the condition is like this, the commutator qi and pi equal to I delta ij, then in this case, the canonical quantization could be easily written down. That is, the phi at x vector and its corresponding conjugate momentum. I will derive the expression for the conjugate momentum very soon. So the conjugate momentum at y is equal to I del x minus y. So that means if x is equal to y, that is, the phi and the pi are at the same point, they are corresponding to the same system, then the commutator is equal to I. If x and y are different at different places, that means it's a different dynamic system. One here, then of course they are not related to each other. Therefore, the commutator between phi here and pi here is equal to 0. This is exactly correspond to this relation. You can easily see they correspond to each other. Okay, and then phi commutator equal to 0, pi wherever they are equal to 0. Done. So quantum field theory is done so soon. Just 2 pages. Okay. Okay, so well, we can finish our lecture. No. I haven't derived the result of this the canonical quantization condition, but you have to trust me. This canonical quantization condition is the endpoint of quantum field theory. We are done here. Okay, we are done here. So that's why I say the quantum field theory is very, very simple. It's very, very simple. However, from there, if you want to derive the result of the canonical quantization condition, well, it takes about another 10 minutes. Okay, it's not difficult if you understand quantum simple harmonic motion well. Why do I say it? You need to understand simple harmonic motion because I will show in this page that the Klein-Gordon field are actually simple harmonic motion. Okay, very easy. What we do is to Fourier expand the Klein-Gordon field. So if phi is Klein-Gordon field, then I do the Fourier transformation, and this is the Fourier. For that, I mean you expand in terms of specific state, specific component with specific p momentum. Okay, so therefore the phi could be written in this way. That's a classic Fourier transformation. And then you plug in this Fourier transformation into the Klein-Gordon equation. And every del square, every space derivative will give you a p. Therefore, this is p squared. So p squared plus m squared, we defined it as omega p. Okay, and it's not clear yet. However, everybody could recognize this is the relation between the energy and momentum of a relativistic particle. Remember, keep that in mind, and it will appear very soon. So this is called, we will call it omega p, and therefore the second term and the third term, after you plug in the Fourier transform, will give you omega p squared, and the first term will give you the second derivative of time, and therefore you get this equation of the Fourier component. Remember, the Fourier component corresponds to a specific momentum with the specific, and every component corresponds to a certain, we could call that plane wave. So this is the plane. This is the Fourier transformation is actually an expansion in terms of plane wave, while this component are the amplitude of it. Okay, if you interpret it in classical way. And after that, from this but Klein-Gordon equation is not just a classical wave or classical field. If you look at this, you easily find that this omega p actually satisfies the equation for a simple harmonic motion. So I put it in red here, that every Fourier component phi p behave just like a simple harmonic motion with omega. Therefore, this phi p has a correspondence with q. The q in the simple harmonic motion I spend the first 30 minutes on. Therefore, you can expect the procedure of quantum simple harmonic motion to apply here, just with some small revision. For example, in quantum simple harmonic motion, I define q as a plus a dagger over square root 2. But here, phi p, I told you phi p will correspond to q. Therefore, phi p will be written as ap plus a dagger, but minus. So there is a minus sign here over square root of 2. And pi p that correspond to the momentum could be written similarly. For this small relation, the reason is that this phi p is a complex number instead of real number for q. So that's why I need to change the sign here from p to minus p. And it could be fine from here. This is to ensure if you plug it into the equation, the phi, you plug it in here, the phi, if you plug this redefinition into phi, then you get this expression or this expansion of phi in terms of a and a dagger. And you can change the sign of the momentum, redefine the momentum as minus p, so that you can, but however, this p runs through all the possible value. Therefore, you can change the sign of the second term to exponential minus IPX, and this will become AP. Okay, so this is the formula we will usually use in the expansion of phi Klein-Gordon equation in terms of A and A dagger. And written in this way, it is easy to show that the phi is actually real. The Klein-Gordon equation is a real number. Here I check for you. You can do it on your own at home. And then the conjugate momentum, I also list its formula here, is also a combination of AP and AP dagger. So now I can right away show you the result of the canonical quantization on the commutation relation between A. Remember, in quantum simple harmonic motion, I use the canonical quantization condition to derive the commutation relation between A and A dagger. That is, the commutator of A and A dagger is equal to 1. The derivation is almost the same. I can simply guess, put a first guess, that the relation here will be AP and AP prime dagger equal to 1 if P and P prime are the same momentum. If P and P prime are the same, then it is equal to 1 because they are the same simple harmonic motion. However, if P and P prime is different, it must vanish because they correspond to different system. Okay, so this relation and this relation is a direct result. You can guess. I haven't derived yet. However, you can guess it must be a direct result from A dagger equal to 1. Okay, so but these could be proven explicitly that the canonical quantization between field and field operator and its conjugate momentum operator will give you this commutation relation between A dagger and AA and A dagger. Okay, so here is the derivation. Okay, so you can do it by yourself. I believe almost every quantum field theory students must do it by yourself once in your life. Okay, so it's not that difficult. Okay, it's not that difficult. Here I derive the derivation between phi and pi using the relation between A and A dagger. Yeah, exactly correct. You can do it reversely. That is, you can assume that this is correct and derive the commutation relation on top. Okay, so it's an exercise. It's no use for me to do it on the blackboard and in online course. Just remember that I only want to cite the result. The result is that the canonical quantization condition is equivalent to this commutation relation between A and A dagger. Okay, so now I can just proceed just like in quantum simple harmonic motion. I leave all the mathematical detail to you, but the final result is so simple, so similar to quantum simple harmonic motion. For example, the Hamiltonian I can derive from here. Okay, and yeah, I probably should put one more transparency to show you how to calculate this. However, H is equal to this combination. And if you put in the expression for pi and phi in terms of A and A dagger, Hamiltonian is equal to omega p A dagger A plus 1/2. So this is exactly almost the same expression of Hamiltonian for a quantum spring, quantum simple harmonic motion. Remember, H is equal to omega A dagger A. Here is omega A dagger A. So it shows you that every P is a simple harmonic motion. That's the bottom line. So every momentum gives you a simple harmonic motion. Okay. And the relation, but the commutation relation between H and A dagger and H and A are exactly the same as quantum simple harmonic motion. Okay, and this also is derivable. So therefore, without further derivation, you can expect A dagger to increase the energy by omega p, and A to decrease the energy by 1 unit omega p. Okay, and therefore that's so here. So the operator A dagger p can be used to raise the energy by 1 unit omega p. And I haven't put in transparency, but you can derive. There is another conserved momentum, which is p. Okay, it corresponds to the symmetry of translation. This p is a conserved number, conserved quantity, and it could be derived as pi grad phi. And if you plug in the expression for pi and phi, it can be easily simplified to p A dagger A. Therefore, this formula expression is very similar to the expression for H, except that the omega p is replaced by the momentum vector. And therefore, by analogy, you can easily be convinced that the operator A not only raised the energy by 1 unit, it also raised the p by 1 unit of p vector. Okay, and the key point is, that the omega p and p satisfy the familiar relation between energy and momentum for a relativistic particle. So here I write in red, so it's important, just like a relativistic particle. Okay, therefore the p state which the A dagger raised from vacuum is a one particle state. Okay, so, and you can do it repeatedly. So I go very, very fast here. You can sit down to think about it deliberate on it in detail. Is so enjoyable. But the bottom line is you can use the A dagger to repeatedly raise the momentum and raise the energy. And therefore, it becomes a particle system. So here I say the A dagger is a creation operator, A the annihilation operator of a particle with momentum P and energy EP. And the momentum P and energy EP satisfy the correct relation of a relativistic particle. Okay, so I'm almost done. See, so that's why the quantum field theory is easy. Here I summarize the 3 steps in our logical derivation. In quantum field theory, every Fourier component phi behaves like a simple harmonic motion with omega p frequency. Then every quantum, in the earlier 30 minutes, I derived the quantum simple harmonic motion does look like a particle system with changeable number. So if you combine these 2 statements, you arrive at the conclusion of the day. Quantum field theory are particle system with variable number, and for every p with the special relativity omega p. Okay, so quantum field theory becomes a particle system. That's the key observation. And therefore, it becomes the cornerstone of all the modern particle physics. Okay, yeah. Okay, so that's it. Okay, I would like to stop here because this conclusion is so important for me. Okay, and I hope you comprehend the elegance of this derivation. Okay, so actually we finished the canonical quantization in less than 1 hour. I do it this way just because I want to emphasize that quantum field theory, in essence, is very, very simple. You just need a field theory, and field theory is like a lot of simple harmonic motion. And if you quantize the simple harmonic motion, every simple harmonic motion look like a particle system. And therefore, quantum field theory are particle systems with variable number, variable particle number for every momentum with its corresponding energy. That's it. Okay, so I will follow up with this lecture with a lecture on some other detail. For example, I can discuss the complex Canonical equation, and then we probably will go on to discuss the cross-section, just like Janus suggested. We'll discuss cross-section and related stuff, and eventually we'll arrive at the Feynman rule and Feynman diagram. Okay, so that will be the topic of next week and the week after next. Okay, so see you later then. Bye bye.